Together. 1, 2, 1, 2. Thank you. So thank you all for being here and for inviting me over. I had a very short trip to come here because we are placed in Berlin for a decade already, and some of my colleagues are here. Well, actually, at Boyd we are running the Neurorobotics Research Laboratory, and we are building robots for, let's say, 10 years or a bit more or less. And so there's a lot of expertise, and I decided for today to just give you one red line, one idea, because an overview you can get on the internet and so on. So there's one robot here, and I will give you one detail which we think makes this robot unique compared to others which you find around the world. So let me also introduce the team members. Unfortunately, only 2 of them can be here today in the evening in relation to the typo conference. Of course, others will also show up. This is also a slide which tells the story that if you do robotics, it's a holistic approach. I mean, you need mechanical guys, you need software programmers, also designers, then psychologists. I, for example, did maths and psychology with my diploma thesis. So without any of them, the robot could not be there. Now, the main topic in the end then will be the Myon robot, or Myon as we say, and there's many stories, and just to skip 2, which I will not go into detail this morning. For example, so here's the inner skeleton and the outer shell. So there's an endo and an exoskeleton, which is a construction detail, which is nice, nice to build electronics into it and being able to add sensors later on. But this is maybe not interesting for now. Something else which is unique, I mean, a humanoid robot is a very complex machine. And normally they are built like, let's say, an airplane. And you would normally just build the whole system and then that's it. And we use the robot not as an application-driven thing. Normally, always people show up and say, "Why can this robot help me with a household, or will it be able to assist in a catastrophe scenario?" Probably robots will do that, but not this one. So this is really a research tool. It's a tool. And we are testing hypotheses about how probably intelligence can emerge. So what are the basic minimal building blocks that could be the pieces you need to put together? So there's several approaches how to discuss this. Of course, you can do it the philosopher's way and say, well, let's just think about it and come up with an idea. And of course, you can do it the psychologist's way, and then you study, well, let's take this girl there, what is she looking at, and so on. Then you have ideas what's probably going on inside. And then there's, of course, the doctors who say, well, let's go into the PET scanner and let's see what brain region shows up if they do this or that task. And we are taking more a synthetic approach. Well, we have an idea and say, let's implement it and see if the system reacts like this. And of course, we need a full-sized robot, or this is a 7-, 8-year-old child's body plan to being able to interact with it. And so one thing was also to build this system so that you can disassemble and reassemble it during runtime. I will not do this now, but we could probably just eventually take off the arms or the head, and the rest of the system and the single parts will still continue doing their thing. And of course, you can also build fancy other stuff. So this is the left arm, just put where the head normally is. And of course, you can play around with arbitrary morphologies. And of course, we also improve body parts. Well, if it's an improvement, we see afterwards, but we think this could be better that way. So in some of the images I show you, you see the gripper is just like a 2-point pinching gripper, and now there are nice hands, and we like them. So the robot is able to grasp objects more firmly and so on. And another story I will not go into, so this is the modularity to being able to put pieces in a different way. And another story I will not go into in detail is we are using a dynamical systems approach, which means that we do respect the dynamics of the body itself. This is demonstrated here. It's like an upright pendulum, and we try always not to use. Let's go back again. We try not to use a central processor which is calculating the motor currents and everything. So it's not like a driven robot from a central processing unit, but it's a reactive system. So the sensors, which are, I mean, there's acceleration sensors, there's angular sensors in each joint and so on, and they are directly coupled into the motors. And then, of course, the black magic is how to do this, but complex movements like walking can be done like that. Of course, we are not the only ones who do this, but this is a very unique approach also, because normally robots coming from industry and other complex robots like the Honda system, they have a model inside the robot and they calculate, I mean, you know this, firstly they go in, bend the knees, and then they do like this, right? And this looks completely different. Just by seeing the characteristics of the movement, you can already tell how it's done. Now, the focus for the next 10 minutes or so will be haptics, because let's think about it. If you watch, if you use ultrasonic imaging and you watch unborns, then you can see that they eventually grasp the umbilical cord and just press it. And of course, they are disrupting their supply channel. And so what happens after a while is that they just fade away a little bit, and then of course the fist opens again and the supply is back there. And if you think about this, this is taking place while the brain is building up, while the neurons are connecting their synapses. So I do not say that the unborn is already aware of that, oh wow, this is my umbilical cord and I can play around with it. But so there are like causal relationships just there in place when the synaptic connections arise, that you use contact and haptics to get an understanding. In Germany we say begreifen kommt von greifen, which means grasping and getting the grasp of something is related very firmly. Now, if we are trying to use a very, very minimalistic, simplistic approach, and this is just one cell organism, an amoeba, and there are movies where you can see that they already do clever things. They can remember periodic events, so if you just tease them every 20 minutes, then after the next 20 minutes they will wait for being teased. So there's papers out there, hit me if you want to know more about this. But so there's a good reason to think that maybe understanding and reaction comes from very low basic things. And we tried the same approach. So this is a simple wire, a piece of wire, and of course you can do a winding, then it's like a magnet. And if you put this, so this could be a coil then, and if you put a current through this, you have a magnetic field, and if you use another magnet, then you get a motor, a rotation, and this is actually just a transfer of the energy from current going to magnetics. Then here you get a mechanical rotation, then you go through the gear, and in the end this can be a pendulum, which of course is the case with both arms and also with the legs. It's just an inverted pendulum. And if you ask an engineer to do a haptic robot, then normally they think, okay, it's about touch and being touched, and you have this in your mobile phone. What they do is they use a touch sensor, and then something's calculated, and they have a vibrating motor to give you some haptic feedback. And this is the way we exactly do not do. We are aware that, and this is very unique with, very special with biological systems, that this way to the arm is of course reversible, and you can move the arm and it goes back. And then you have here a voltage which is proportional to what you do with the arm. And engineers normally build systems which are not reversible all the time. Of course, if you use some special gears like snail gear, then you are not able to drive the arm back. So being able to go back and forth is the key for that. Now I will show you some videos. We built a system which is not using sensors and which is always going against the force. So this is a simple Lego motor. Here's a small electronics. There's no computer and nothing digital in here, or not necessarily. And as you see, this motor is driving the pendulum upwards. Oh, this is an easy thing. You could think it's, by the way, not slowed down, so this is the original velocity. But something interesting happens now. Namely, if you touch this, and of course this is all plastics, so there's no sensor in there, it's just the motor goes back through the wire to the electronics. Then you can stay in touch with the system without any sensor. And the advantages are, of course, can be clearly seen. If you take apart, let's say, the upper part, you cut this off, then the rest, the remaining thing, is still able to do the same trick. If you would attach a sensor for touch there, then if something is broken, the whole behavior is gone. And this is a kind of robustness, reliability, which is, of course, very important for a complex system, because there can so many things go wrong. Maybe in the end, when we want to demonstrate something, it will not work. So this is a surprise that we have to deal with all the time. So the touch without a touch sensor is something unique. And maybe before we get to the real robot, if we use the very same system and it's not able to lift the slightly heavier weight by itself, we could think, well, maybe we can help it. And of course, the same force is needed in this and in the symmetric position up here. So I try to lift it up there in the hope that it will continue from there, but it does not. It's like a stubborn thing. But interesting thing, if I do this very gently, like here, so a bit slower, then surprisingly, it will take over. So principles like help to help itself arise here, and the bottom point is that we did not put this in. We just played around with this simple mechanism and felt like food intake or stabilizing the body and stuff like that is just in there. Now, let's get closer to the robot. We put this very same Lego principle on the join of this leg. It's actually a leg of this robot. And it's going against the gravitational force, so it tries to get up. Of course, it's not possible, because always if one part of the leg is upside, it will turn around. So it's a bit, we're giving this leg a hard time. But here you see, it's just the advantage of having a modular system, that you can play around with the parts. We are not yet into ethics question, because there's no awareness here, but at some point, maybe in 10 years or so, we will have to rediscuss this. Yeah, it's actually, the whole robot is 15 kilograms, so it's very lightweight. But of course, if you hit this, if this thing hits in the face, it's no fun. Yeah. This is, of course, clear. So now, the interesting thing is, now this was one joint. Now this leg with the shells has 3 joints, 1, 2, 3. And the same principle going against the force makes the whole leg stand up by itself. And this is something very surprising, because the point is that there is no communication between these joints. So the mechanisms are completely local. So we are collaborating with Shunji Yamanaka-san in Tokyo. So he's a design professor who has a huge team of students, and they built very fancy, arbitrary shaped robots, and we just put the principle on that, and then they just stand up. I mean, you don't think about the morphology, you just put the principle, and then they try to stand up in different ways. And it's a self-referential system, so there's no target angle and there's no main processor who gives the direction. It's just interacting with the environment. And we feel like this is, you see, if he takes this up, then the rest, the things that are allowed to move, they go up and try their very best to go against the force. And there's, of course, Also other things, for example, if the leg is not able to stand up at the first try, then the leg retries a second or a third time until it succeeds. You will see this right now. In the first try, it just contracts, but it will not succeed to fall onto the foot. So it goes reverse direction and tries again until it succeeds. And then also inspect yourself while you're standing. You never stand like a machine upright. You're always sensing gravity by leaning a bit forward and backward. You're waving a bit on the ground, and this is exactly what this leg is doing. Okay, so I guess it's now time to see this in live action. So my colleague Markus Jans will, before you start, I just tell what we will see. So this is an interaction where he helps the robot to stand up. And the problem that we always have with this thing is that the audience says, well, this is trivial. We sit, we stand, what's the deal with that? But if you go into detail, of course, standing means that you control like 50 motors in a ordered manner. And of course, babies need like 1 year before they're able to really stand in a stable way. Of course, your child was able to do it in 10 months, but I mean, in the average, well, the others then speak earlier, so it's so maybe if you go out somewhere, try and watch a love couple or a mother with a child. So if they go hand in hand, okay, sometimes the mother is really dragging the child, but normally in a relaxed manner, it's dominating and going along. So the role in a nice relationship, the role always changes. So I mean, you lead a bit to there, and then you find, how did we get here? Well, I don't know, but we made our way together. So here, while helping the robot to go up, the joints need to decide, do I put a fourth into it? Of course, you are not able to help the robot stand up if you're just dragging, or it would be really horrible for the machine. So you have a tension in the arm. But then, of course, at some point where the robot is already almost standing, the tension is in the way. I mean, if you then do small movements, you destabilize the robot and you will likely make it fall over. So at some point, the arms have to decide to let go. And this is the case also for all the other joints. So of course you will not do it in a slow motion, but just to give you a way what to look for and what to watch at while you do it. So let's go for it. And the robot will also say what. Okay, so this is standing stable, ready now. Of course, the internal states of the robot we just put to a speech system so that we know what's going on inside. And now maybe you show some things that the robot can do. For example, the sensory system going for motion. Maybe you saw this already while you were coming in. Or maybe we could try sound. Here. Or no. Well, actually, I was maybe. Well, okay, so you see, it's already a bit of an own will, and so there's different systems which are working in parallel. There's a motion system, then there is, of course, shapy and colorful objects. Then there's sound. Normally, this works pretty well, but of course, there's a lot of reverberation here. And of course, the speakers are the sound sources and not where I'm standing. Normally, if I don't use the microphone, it's easier for the robot to locate. And here you see, just to conclude, these slightly waving motion. This robot will also take role in the opera called My Square Lady with the Komische Oper in June, July. And they have a raked stage. It's like 5 degrees or something. It's quite something. And so because it's self-referential, it's able to balance this out, and so we can just move the robot around. Okay, maybe do you want to show something else, or so I would then open the stage for questions, and thank you again very much, and ask what you like to know. Yeah.